Now, the last thing we're going to deal with today, bad measurements. Sometimes the equipment fails. Sometimes your receiver in the field doesn't communicate back to the base station. Sometimes the hard disk crashes for a few minutes and then it comes back. Bad data is going to happen at some point, and there's a serious consequence if you ignore that. So we have 3 data points here that do not fit the rest of the data, and we can imagine explaining those as some kind of measurement failure. Let's talk about the linear fit we get with this and see what the effect of having that bad data in there is. There we go. So, oh my god, those are so small. Let me just boost the size up here because there are dots there, but they're almost invisible. Let's make them really big. There we go. Okay. So those are our data, and we can see the 3 points that failed, or maybe more. Maybe there's overlap there. We can't really tell. We're going to fit that with our tools, basic fitting, and we're going to get a linear fit to that. That's fine. And we're going to plot the residuals as a scatter plot and see the result. So this one is actually the effect of having those 3 points at the bottom is actually so strong that you can see all the data points that are real, the ones we'd understand as being real, are above the line. My line is not going anywhere near the actual data points of real data. It's being dragged south, it's being dragged down because it's trying its best to fit these 3 data points into the picture. And because they're so far away and we're squaring that error so it becomes even more magnified, those 3 points have a huge effect and they're dragging the entire line down to something unrealistic. If we found the coefficients of that line, they'd be completely meaningless because they don't describe the good data here, right? Now this, I will admit right up front, is a case where the bad data points they're beating you over the head. I'm bad data. Now, that doesn't always happen. You might have a point up here, say, like, it's out of the range, but it's not totally crazy. And then you get into one of these debates about how much cleaning do you do on your data. In this particular instance, I'm pretty sure those zeros are wrong. I can attribute a cause to why they're wrong. The machine failed. So it's much more legitimate to just say, I'm going to ignore those, let everyone know that I did take those out. So what we're going to do is take advantage of that knowledge and actually remove the data set, or remove those points. For nomenclature, Gesundheit, these are called outliers. Anything that doesn't belong, in whatever definition of doesn't belong you want to use, we would call an outlier, and one of the ways to deal with them is just to take them out of the data set before we fit things. All right. The nice thing about the residual plot is it really, really, really highlights the residuals. Most of the data is around 0. Oh, wait, except for this dot, and that dot. Those clearly do not belong to the data set in terms of the range of variability that the rest of the data displays. So the residual plot is a good way to identify outliers. So once you identify them, the simplest solution is to remove them. And you can delete them manually by going into the data set. That's a little sketchy. But a better way is to say, here's a filter I'm going to apply, and here's the filter I did apply. Trim the data down, and then recompute the fit. So one of the things we can do with our particular data set is say, well, all the values here that are real, the ones up here, the ones we believe are true, are above 0. So we can actually use that same logical filter and remove the outliers with a little test here. Now, I don't know if the values are exactly 0, like 0.5, but if I look at the range, they're all below 10. So an easy way to filter would just be, pick a criteria, threshold. I'm going to keep all the values that are greater than 10. And notice I can do this. This is a short version of what we did before. We could have built the filter this way, build a vector of all the pressures that are above 10, and then filtered with this V, and that would have done the same thing. Key thing, though, is subselect your P's based on some vector of yes and no's, subselect the matching temperatures based on some vector of yes and no's, and those yes and no's are my pressures above 10. And when we do that, we get a cleaner data set, and I think I got my order wrong. Yeah, we had temperature on the axis here and pressure on the other axis. Let's do that. And there we go. Newt. Now, capital T. One last go around. There we go. So there's our cleaned up data set. They're hard to see before, but there are not dots down here. And now when we do the linear fit, it's going to make a lot more sense. So we take our linear fit, and I plot the residuals as a scatter plot. Scatter plot. Now we have, actually, we're back to the same problem we had before, but we see that the line is going roughly through the data now. It's not being dragged south, dragged down by those outliers that did not belong to the data set, so why were we fitting a best fit line to them? Then we get back to the same problem we had before, which is the spread of the data out here is much, much bigger than the spread here. And we start doing one of those multi-stage cleanup operations where stage 1, remove the outlier. Stage 2, the fit's still not the best. We should really take the log of the data set so that we get the variability consistent. And log t versus log p again. So we're going to do the same steps again, and when we do that, we start seeing consistency in the data. The variability is about the same at the start as it is at the end. Now I can do a best fit line. It'll make sense because it was percentage error that's now additive error. All the same messages we talked about in the previous example. So let me just go back to the code for a sec, show you what happened in those two transformations. We got the temperature and pressure. We removed the outliers with a logical filter. Anything that has 0 pressure or less than 10 pressure got thrown away. Everything that was above 10 pressure got kept. And then once we did that, we filtered. As far as that worked, actually. That should have actually been new P and new T. Newts. All right. And that's it. That's the process. One of the things to mention is least squares is just, again, one option. It was invented because it gave unique solutions, and back when we didn't have computers, that's what we could actually solve for, the least squares fit. It turns out that now that we have computers that can do optimization and can use absolute values instead of squares and still get through the calculations, there are actually fitting techniques that work better than just this, I'm going to throw an outlier out, not throw an outlier out. How do I define an outlier? If that's a thorny issue in whatever area you're in, it probably means you should use a different technique for fitting, not that you should overstress the outliers. So there's a whole, it's actually a subdiscipline of statistics, this idea of fitting with not least squares. So keep that in mind as you go forward.